this video we're going to talk about RL and the Sorgenfray plane. RL is the typical example of a Lindelöf space, and the Sorgenfray plane is an example that shows us that the product of Lindelöf spaces is not necessarily Lindelöf. Let's start with RL and prove which of the countability axioms it satisfies. It's very simple to see that RL is first countable, because given any element in RL, we can always find the basis x plus 1 over n for every n natural. This is obviously a countable set, and it's a basis at x. So RL is first countable. Now let's see if it's second countable. We want to see if RL has a countable basis. For this, let's suppose that we have a basis B, and let's see if this basis B can be countable. For this, let's make use of this local basis at each point in the real numbers. Given any element in the space, we can take some basis element B. Let's say that B depends on x, such that x is an element of Px, and Px is contained in the set x plus 1. That's because P is a basis, and this set is just any neighborhood of x, so there always exists some basis element Px such that this happens. So we have a function that for each x, it returns this basis element Px, and this function is injective because if I take another element in the space, let's say that y is different from x, then Bx will be different from By. This is very easy to see if we draw it. Let's say that here is x and this number is y, and set y plus 1 is going to be something like this. So none of this is a subset of the other, meaning that the sets that we grab, Bx and By, will be different. And that proves that this function is injective. But now we have as many elements x as numbers we have in the real line. So this function is injective, and so that means that this basis has to be uncountable. And with this, we know that RL is not second countable. Now let's see if it's separable. It's very easy to see that the rational numbers are tens in RL. And obviously the rational numbers are countable, so this would mean that the space is separable. And the rational numbers are tens in RL because if we take any x in the real line and consider some neighborhood of that element of the form x plus epsilon, we know that there will always exist some rational number q that is inside this interval. So try and write this proof better, but this is essentially showing us that these elements in the real line are in the closure of the rational numbers, meaning that the rational numbers are tens in the real line. Now let's see if it's Lindelöf. To show that a set is Lindelöf, we have to take any covering of the set and prove that there will exist a countable subcollection that also covers the set. And without loss of generalization, like we did with the compact sets, we can take this covering to be formed by elements in the basis. So we will take a collection A alpha, P alpha of open sets in RL that cover RL. We need to extract a countable subcollection of this set. What we're going to do to show this is the following. Suppose this is our space. I know RL is usually a real line, but just follow me for this. What we will do is divide this set into two parts. and then show that one of these parts is countable and that this other part can be covered by a countable subcollection. And so with this we will have that the total space will be covered by a countable collection, because we could just cover all of these, each element, and because it's countable, then this whole collection would be immediately countable. So let's do this. The way we're going to separate this space is by defining some set C to be the union over all the alphas of, instead of closed interval in the left extreme, open intervals A alpha, B alpha. And the separation of the space that I mentioned here is going to be C and RL minus C. So now let's prove first that R minus C is countable. For this, let's take, well, if we take some element in R minus C, that means that X is not in any of these intervals, but the intervals with the closed extreme form the cover of RL. So that implies that X has to be A alpha 0 for some alpha 0. Now we will have a look at the interval A alpha 0, B alpha 0. This is just any interval in the real line. And so, for this interval, there exists some rational number, Qx, that is contained in there. So Qx is an element in A alpha 0, B alpha 0. Then the interval A alpha 0 Qx, this is the open interval x Qx, is contained in this other one. But if we take another element in R minus C that's different from X, then we could also choose from this, in the same way we did here, the Qi. If Y is different from X, we can suppose that X is less than Y, then this implies that Qx is less than Qi. And this is because if we had X smaller than Y, smaller than Qi, less than or equal to Qx, then we would have that Y is an element in X Qx, which is a subset of A alpha 0, A alpha 0 is X, and B alpha 0. And if this happened, then Y would be an element in C. But we took Y in R minus C, so this would be absurd. So this is why we have this implication. And now we have that for each X in R minus C, we have a function that gives us some element Qx that's rational. And so, because these are countable, that implies that these elements have to be countable. So, R minus C is countable. Perfect. This helps us for this first part. Now, we have to prove that C admits a countable cover. For this, we will consider C as a subset of R, but with the standard topology. Now remember that the real line with the standard topology is second countable, and that implies that C will also be second countable, but with the standard topology. So this implies that we can cover C with a family of open intervals. And so all we have to do is now consider the family, the intervals with now the closed left extreme and open in the right. Now this family will give us a countable covering of C in RL. So now that we have finished finding this countable cover, we have finally that RL is Lindelöf. This example helps us also to prove that a space can be separable or Lindelöf without being second countable, because we know that the other implication was true. Perfect. Now let's see what is the Sorgenfray plane. The Sorgenfray plane is RL times RL. And we will see that it's not Lindelöf. For this, we will consider a specific subset of the plane. So if this is RL and RL, we will consider the set L formed by all the elements of the form minus x times x, where x is a real number. So L is this diagonal. Well, it's easy to see that this set is closed. That implies that RL squared minus L is open. Now, to prove that this set is not Lindelöf, we would have to find a covering for which there is no countable subcollection that also covers the set. And so, because RL squared minus L is open, we can cover the plane by using this set and a covering of L. And we can take, for example, a covering of L of basis elements. So we will consider the covering So this is a covering of L. This set here is covering L, because all these sets are squared like this. So they are touching L at each of these extremes. But this covering will not have a countable subcover, because we need one of these for each number in this diagonal. And this diagonal is obviously uncountable. So for this set, this shows us that for this covering, there is no countable subcollection that covers RL squared. And with this, we finished the video.